July. So we're going to go see Kevin now in his experiment to see what it actually looks like to have a telescope mounted on a rocket that's going to be coming down via parachute later next week.
If there's a little bit of residual gas in there, you can actually create an arc that goes across the small amount of gas. It'll act like a conductor. And if that happens, then things can break down and melt quickly.
I can imagine that.
So there are all sorts of inhibits on here to not let the detector turn on if it's not at high vacuum. And in fact, we actually during flight we take this. When we're arming the vehicle, we take this plate off and we put a little cheater plug in there that allows it to override that circuit, so it will turn on in flight no matter what.
Oh, okay.
But then it's very dicey because if somebody accidentally turns it on, it would be very bad. So it's like it's only held safe by humans at that point, which is a scary thing.
Which is always a trick. So the telescope is here?
That's right. So the telescope starts here. It points out this way. This is what we call the shutter door. If you see, it's on a thread here. And there's a hinge down here. And in flight, on a timer, this motor will run. It'll run the thread down and open the door this way. And look out, and the telescope will look out.
So essentially, this is the bay door that opens up, and then you're looking out this way.
That's right.
So then, so the telescope mirror width is maximized.
That's right. It takes up the whole thing.
I assume that was it.
It's a full half-meter mirror, which is so the diameter here is 22 inches, and the mirror is like 20.5 inches. So it's as big as we could possibly go. We wanted to make these measurements of Alpha Cent, and we realized that we couldn't have done it with previous technology that you could have put on a rocket. And so we said, well, actually, if we use these advanced technologies, we can build this instrument that will have, throughput 15 times greater than what we'd ever been able to do before, and we can actually do this science even on a rocket payload. And so we just, built it all together.
Nice. Well, look, so far, it seems like it's tracking well, at least.
This is also the second science flight. We did a test science flight to observe an F-type star in November of last year.
At White Sands.
NASA did not want this to be the first flight of these payloads.
Interesting.
Yes, they wanted payloads that had a high probability of scientific success. Which I completely understand.
You don't want 3 missions that go up and don't give data because.
That's right. This was a big investment, and so we wanted to make sure that we got the bang for the buck.
It makes sense, right? I mean, because it has not just been you guys coming here; it has been
the whole
everything.
Enterprise. Exactly. Which has been fantastic.
Which normally you're just dealing with the individual experiment, right? In terms of, especially operating from the U.S., where here, for these 3 missions, it is the whole enterprise of the facilities, getting him here.
Exactly, and when we launch in the U.S., we basically just plugging our experiment into a process that is already happening. Here, we've created the process.
Yes, exactly.
And so it's just a much bigger undertaking, and so we wanted to make sure that we'd work the kinks out.
I understand. Did you get data on the first flight?
It was beautiful. We have my former my almost to defend grad student now is back at home writing the paper on that data.
Awesome.
22 minutes.
So that is kind of the second payload that we'll start to see up close. Well, not for this launch, but on a second launch on 4 July. We'll then have the third launch on 12 July. Now, obviously, we weren't able to quite show the first experiment. That's because it was already loaded to the rocket. And once it's integrated with the rocket, that's what you're seeing here on the launch pad. This is the integrated rocket. Now, you can just make out the gantry. That is the metal support structure on the left. So that is actually what's holding the rocket in place. Now, this is a sounding rocket. Now, what we mean by sounding rocket is it goes into orbit, but it doesn't do a full orbit around the Earth. You can also see a few of the raindrops still on the camera from that beautiful dry season rain we had earlier, but it will be blown off when that rocket takes off. Hopefully we still keep the camera, but that's someone else's problem. Now, as that rocket takes off on the right, you can see there's actually going to be different stages. And in a little bit, we'll go to an earlier shot that we had today of the rocket on the launch pad during the daytime so we can see the different sections. There are multiple stages to this rocket. There are stages that involve the motor, i.e. the engine getting up. There are stages that just contain the science payload. And that's kind of what we saw in the lab earlier with Kevin. That is the part where the telescope, all the electronics, the equipment is. Now, the engine part, the motor part, is that first bottom part that you're seeing now attached to the gantry on the left. And again, we apologize for the kind of distortion of rain on the lens, but that's what's happened with the rain, and we can't obviously have anyone down there to dry it off because it is a working site, and they are preparing for launch now just under 20 minutes. So we originally were scheduled for a launch 10 minutes ago, but that was pushed back through a 30-minute delay. Again, fairly normal. There's been no other changes or issues to this. It is a normal check that they do because this whole countdown is an 8-hour process. So sometimes during that countdown, you have to make sure things are double checked. Again, safety and success is the priority of Equatorial Launch Australia and NASA for this mission. So that means sometimes you just have to delay things. But luckily, it's only 20 minutes to go, not even that, before we see this launch take place. Now, when you look at this rocket, what you'll see is when it launches from our shots that you'll be seeing later, it will be launching towards the southwest. So as viewed from now, it's going to be going slightly off screen to the right. Now we'll have further cameras back that will follow up for as long as we can. Now, this rocket actually does move fairly fast. Because it is a small sounding rocket, it does actually move quite quickly, accelerating on that initial go. And now, sounding rockets are actually quite common. We're kind of used to these giant rockets, but a lot of these missions at places like NASA Wallops facility, who is the partner with Equatorial Launch Australia, they're the customer here launching this rocket or having the rocket launched. They do launch from all over. They've launched from Alaska, White Sands, New Mexico, Svalbard in Sweden, and almost everywhere in between. This is their first commercial launch anywhere, though. Usually when they've launched, it's been a government or national or military facility, so to speak, something not operated purely by a commercial entity. And I think that is part of the story and legacy about what we're seeing tonight. And that is Equatorial Launch Australia's vision was, if you build it, they will come. If you build a great facility that has all the requirements for what a rocket wants, you will have customers like NASA wanting to come to your facility. Now, it's not easy. When you build a spaceport, you have to have a few different bits of infrastructure. You need to have communications. You need to have data. You need to have electricity, power, places to houses. You know, you're building in somewhere that is one of the remote locations, not just in Australia, but probably in the world. And you're building some of the most sophisticated experiments that scientists and engineers can do. Now, one of the great things about that is it prevents and gives unique possibilities. It prevents